Hello everyone, my name is Anthony and this is the series of how to get started making your own quadcopter. And today what we're going to talk about is the flight dynamics and control, how to mathematically model a quadcopter. This is a series of 6 videos where the first 3 videos were all about the embedded stacks of how you can build your own quadcopter, a high level overview of how you can make your own quadcopter. And then we started to focus on things like sensor fusion, and now we're getting into the mathematics of how do you make what the quadcopter could be represented through mathematics. In here, we're going to talk about how to create a mathematical model of a quadcopter. Before we start to build a quadcopter, it is good to understand how a quadcopter works. A quadcopter has 4 motors, and based on the 4 motors, the quadcopter can fly either translational or rotational. Let me explain what do I mean by translational. A translational motion could be something such as an up-down motion. A quadcopter can also move left and right. And it can also move front and back. These 3 motions are generally considered translational. Rotational motion is when it's moving across an axis or rotating across an axis. For example, when you want it to roll across an axis, now it's moving and rotating across, say, the x-axis. You can also make it rotate in the front and backwards axis. Now, this is not the perfect animation, it's 2D, but the goal is it can pitch in the forward or backward direction. So it's rotating across the y-axis. And last, it's also able to rotate across the z-axis or the vertical axis. In this particular case, from the top view, you can see that it's moving, and we call that the yaw. So you can see that the quadcopter can move up, down, left, right, front, back. It can roll, it can pitch, and it can yaw. And you are able to make the quadcopter move in these 6 ways just by controlling 4 motors. So that's the reason why when it's rotating across an axis, we call them rotational. And when it's moving, say, from one point A to point B, we call them translational. Those are the 6 ways in which a quadcopter can move. So how does each motor make the quadcopter move in a particular way? So let's try to find the correlation between, say, motor 1, motor 2, and motor 3, and motor 4 with how it rolls, how it pitches, or how it moves back and how it moves forward. A quadcopter has 4 motors. Let's label them M1, M2, M3, and M4. If you want to make the quadcopter move up, you need to make all the propellers move at the same speed, and it needs to rotate at a pretty high speed so that the forces that it generates is greater than the weight of the quadcopter, and also greater than the quadcopter plus the aerodynamic drag. So a quadcopter, once it starts to rotate, once the blades start to propel, it needs to generate enough thrust so that it can move up. And if you want it to come down, you just basically lower the speed. If you want the quadcopter to move, say, left or right, then you need to make, say, for example, if you want to make the quadcopter move from the stationary, from a hover position to the right, you will make motor M1 and M4 move at a higher speed than motor M2 and M3. And this is how it would look like. So it will first tilt and then it will move towards the right. This is necessary because a quadcopter has 4 inputs, but it can have 6 ways of moving. And because there are more outputs than there are inputs to control it, you generally consider this quadcopter an under-actuated system because there's more outputs and less inputs, which means for every motor configuration, there is not one that directly relates to, say, a particular translational output, in this particular case, moving right. So in order to move right, the quadcopter needs to first tilt, and because of the tilting action, it then moves towards the right. This is how you can control the quadcopter for it to move in different directions. Similarly, if you want it to move left, the quadcopter pitches or rolls, and then it moves left. It's this roll action that allows the quadcopter to move in the direction you want it to move. And similarly for it, if you want to move front or back, you change the speed of the first two motors, which could be M4 and M3, and then you increase the speed of motor M1 and M2, and then that would make the backside of the quadcopter move a little higher, and the front side will be tilted in a little lower, and that will allow it to propel in the forward direction. And if you want to move it in the backward direction, you have to just change the motor speed of M1 and M2 and M4 and M3. Similarly for yaw. And yaw is when you're moving and rotating the quadcopter across an axis. In this particular case, you have two quadcopters propellers, the opposite side of the quadcopter, which is motor M1 and motor M3. Those propellers move in one direction, and motor M2 and M4 rotate in a different direction. So M3 and M1 will have the same rotational direction, and M4 and M2 will have the same rotational direction. And this is so that we can counteract the forces. So for example, if you want to make the quadcopter more stable and you don't want it to rotate across its axis, you need to put the propellers rotating in different directions, the opposite propellers moving in one direction and the other opposite propellers moving in the other direction. If you don't do that, then the quadcopter will suddenly start to have a rotational effect, and it might either start spinning across its axis. It can either spin in the clockwise or anti-clockwise direction, and we don't want this to happen. So to prevent the rotational force, we need to counteract that, and that's the reason why we have two propellers in the different direction. So this is how it would work. So if you wanted to move in one direction, the propeller that is moving in the anti-clockwise direction will need to be at a higher speed than the propellers moving in the clockwise direction, and that's how you can make the quadcopter move anti-clockwise and vice versa. So now that we know how a quadcopter moves or rotates and how it can navigate, change position, translational and rotational, let's go now into understanding how we can create the model of the quadcopter. How do we control this quadcopter? A quadcopter high-level block diagram. You have an input. An input could be the moving up, moving down, moving left, moving right. You want it to, spin across an axis so that, for example, you want to take a camera shot that's 180 degrees behind it. So you want it to rotate across its axis 180 degrees. You want to maybe perhaps find the location of where the quadcopter is at a particular instance. So there are certain inputs that you can give to the quadcopter. And in this case, let's keep it simple, and it'll be like move up, move down, move forward, move back, move left, move right. That input signal is then fed into the flight controller. We will not talk about the flight controller in this video. We will get to that, but just think of it as a black box which gives in information, which takes in the input from, say, a human interface through the joystick that you are using. That input signal goes into a flight controller and it translates into what should be the motor speeds. So let's give it at a high level overview that the controller is taking some random input signal. I won't say random, but it's taking your input signal and translating it into how do I need to control the speed of the motor. And it then gives directions to how it wants the speed of the motor to rotate at, so that the quadcopter can move in the direction that the user wants. And while it's controlling the motor speed, the quadcopter is clearly going to, physically interact with the world by moving up, left, down, right. And that orientation or its movement is now tracked through sensors. And a quadcopter could be filled with different sensors, such as an IMU, a pressure sensor, a GPS for measuring position, power and voltage. If you can measure the power and voltage, you can somehow measure the energy of how much power it's consuming. You can also measure the speed of the motor through the voltage and current from the electrical input of the motor. Optical sensors, so that you can measure the speed of the propeller blades. And you can also equip the sensor, the quadcopter, with computer vision capabilities like camera, LiDAR, radio. For radio, you can find the direction of where the radio signal is. So you can do a lot more complex stuff by the sensors. But let's focus mostly on the IMU. The IMU gives us the attitude of the quadcopter, which tells us how the quadcopter's orientation is with respect to the ground. This is then fed to the sensor fusion algorithm. And the sensor fusion algorithm should tell you exactly what the orientation of the quadcopter is. It should tell you whether it's moving, whether the quadcopter is in 30 degrees, 40 degrees with respect to the Earth on its x-axis, maybe 20 degrees with respect to the Earth in the y-axis. So it needs to give you the high-level orientation of the quadcopter. So that's what the sensor fusion algorithm will do. And once we get the sensor fusion algorithm, take that feedback and bring it back to the controller. And the controller will now measure the error difference. It says the input is giving us to move up, and the quadcopter is not quite moved up yet. And based on that, it'll try to correct the error and then make adjustments to the motor speeds. And again, this loop will continue and continue and continue till it matches the input, till the input matches the output. This loop will go on and on and on. So this is the high-level overview of what's happening inside the quadcopter. But the real question is, how does it know what speeds it needs to do? It needs to give. It needs to, what signals does it need to send to the quadcopter so that the speed of the motors do not make the quadcopter crash or do not make the quadcopter unstable? This is what we're really trying to accomplish. When we try to get the mathematical model of any system, we're trying to figure out what is the ideal way in which a controller can feed inputs to the system so that it does not crash. It's not unstable. It's not bouncing all over the place. It's not moving in a way that it's not supposed to move. That's what we're trying to accomplish over here. Because it needs to make fine adjustments with controlling the speed of the motor, that you need to kind of understand how the quadcopter works so that it can make fine adjustments. And that's what we're trying to do by creating a mathematical model of the quadcopter. So let's understand, how do you create the mathematical model of the quadcopter? One thing to understand is, what can we measure from the quadcopter? Just based on measurements, what can we measure? So one thing we can measure is the force and torque that the propellers generate when it spins. So you can basically figure out what's the force of motor 1, motor 2, motor 3, motor 4, and correspond the speed with this rotational speed with the torque. That is the amount of force it's generating when the quadcopter spins across its axis, and how much force is generating so that it lifts the quadcopter. You can measure those quantities. You can also measure the propeller aerodynamic force. For example, the drag or the wind. If you start putting in you start subjecting the quadcopter to a lot of wind, how does it behave? How does the quadcopter able to counteract those measures? If it's not tested, then you might want to test that. You want to measure the rotational torque. You want to measure the moment of inertia, the weight of the quadcopter, where's the center of gravity. And there are also different types of configuration. So a quadcopter could have the X-type configuration, which we have shown you, and could also have the plus-type configuration. You can also measure the angular acceleration and linear acceleration. Angular, it's the same thing as talking about the translational motion as well as the rotational motion. As you can see, there's so many different quantities, and all of this can be subjected to different frequencies. For example, I can make the motor move at a very high speed, at a very low speed, and I can keep changing this very quickly to see how the quadcopter behaves. So now I don't have to just subject it to one particular speed, but if I keep changing the speed, how does a quadcopter behave? So then you're not just doing single instance and mapping input to output, but you're also mapping now frequency, the change in input, to how the quadcopter behaves. And that's what we're trying to do. We're trying to understand the system. So you have an input, and you're trying to have a mathematical representation of the quadcopter, and then you're trying to measure the output. And the input could be the motor speed, and the output could be something else. And this mathematical representation of the quadcopter is generally done using either Laplace transform, which we call them transfer functions, or a state space model. A transfer function is generally a single input, single output. So for example, you want to measure the speed of the motor with the propeller on, and how does, say, the lift force corresponds to the speed of the motor. Whereas in a state space equation, you can have multiple inputs. So you can have motor 1, motor 2, motor 3, motor 4, and how they behave, how they change, how the changes in the speed of those motors can, correlate to the lift force, the rotational forces, and every other parameters. So there is two different ways of representing a quadcopter. One is more simpler, but it only focuses on a part of a quadcopter, whereas one can take the whole quadcopter and put them in one equation. So let's try to understand a little bit more about what we mean by a single input, single output system. So a single input would be like, let's take for example motor 1, and we're trying to change the speed. And you want to change the speed because you really want to graph how does the motor behave across a wide range of frequencies. All right. And a Laplace transform, which is also known as a transfer function, is great if you want to map, say, motor 1 with, say, angular acceleration. So an angular acceleration would be something like the quadcopter moving from one on its x-axis and how it's rotating and moving around. And you're trying to measure the angular acceleration. How quickly does it rotate? Because we're just measuring one motor. And then you basically jot down all the parameters of the angular acceleration. And based on the input and output, you'll be able to get an equation. And it's that equation that mathematically represents the quadcopter. Without having a good understanding of measurements, it becomes a very theoretical subject of just, designing a quadcopter based on, high-level parameters. It is much more better to conduct experiments so that you have a more concrete understanding of what you're measuring, and then from there build up the mathematical model. But this is how you go about designing a mathematical model of a quadcopter, because once you understand the mathematical model of the quadcopter, then the controller, which is controlling the speed of the motor, would know exactly what to do at a particular situation. When you say go up, move down, move left, move right, it'll try to keep the quadcopter stable by controlling the speed of the motor, because it understands how the quadcopter is behaving. And without understanding how the quadcopter behaves, it would not know how to generate or how to change the speed of the motors so that it's stable. And that's the reason why we need the mathematical model, because of this. And the same thing with state space. You can conduct different experiments. As I mentioned, you can accommodate motor 1, motor 2, motor 3, motor 4, and then you can have and measure different or more varieties of outputs. And then you start mapping them. And then you make sense of those equations and say, okay, what is the input doing and what would the output doing? You might want to change the propeller. You might want to change the pitch of the propeller. You might want to change the length of the diameter of the propeller. You might want to have a 2-blade propeller versus a 1-blade propeller. And because the propeller is the one that is converting the rotational force into an actual flying object, the propeller design really makes a huge difference, because the quadcopter equation wouldn't make any sense without a propeller, without accounting for how the propeller works. And including the material of the propeller. When it rotates quickly, how much vibration does it generate? How stable is it? So when we talk about mathematical representation of a quadcopter, it is, in my belief, in my honest opinion, without conducting proper experiments, just blindly solving equations, which you'll find a lot of papers talking about how they can, from first principles model a quadcopter, I would generally avoid representing a quadcopter that way, because then it becomes a toy and you really will make an unstable system. And if you want to make it extremely stable, it's very important to perform experiments and build up the equations from the grounds up by understanding basic phenomena of physics. I don't want to get too much into the equation, at least not in this video series, but later on we'll talk about doing the experiments and figuring out how we can fine tune and come up with a great mathematical model so that we can make our quadcopter much more stable. If you like this video, I highly recommend you to subscribe or like this video, and until next time, thank you.